Hello. For the third time and for the last time, we will look at numerical methods for solving initial value problems for differential equations of order 1. We will introduce two new ideas, two new viewpoints. And for the first one, we will actually have to change the whole setup. We will change the way that we see the world. Here it comes. When we are solving an initial value problem, we are really looking for a specific function. Here is a particular solution which starts at the location x0, y0, and we talked about really looking at it on just some interval, going to x0 plus t. And when we draw a picture like that, or when we talk about a function, we are actually sending a message that we perceive the world as a continuous entity, which is not a bad idea. I mean, let's say that I'm walking now. I walk a lot when I teach. It's my daily workout. And as I'm walking, I'm at a specific position now. And a while later, I'm at a different position. And as far as I can tell, I actually passed through all the intermediate locations. I am not aware of making any jumps in space, like I'm standing there, and the next moment, I'm standing here, although it could be fun. So this is really the way we see the world, as something which changes continuously. And this is a very good viewpoint because it opens the door to calculus. We can use all tools from calculus, derivatives, things like that. These are extremely powerful tools. So this is a good viewpoint. However, one wonders. Let's say weight. We treat it as a continuous entity usually because we measure it using decimal numbers. But the matter is actually composed of atoms. So take a piece of solid gold. Sounds good. And there could be 13 atoms or 14 atoms. And that's it. Nothing in between. 13.5 atoms, nothing like that. So there are two specific weights, and there is no weight in between. So actually the allowable weights for solid gold, there's essentially a finite number of them if you are limited by weight, let's say. So this is a discrete situation, a situation when you cannot pass from one value to another continuously. And there are more inspirations like that. I mean, take the whole quantum physics. It sees the world really as moving in chunks. So this is another perfectly valid viewpoint. And how can we change from continuous viewpoint to a discrete viewpoint? That's the key idea for the first approach. Well, we have to start with this independent variable. We can imagine that it's time. And we are going to pass from a continuous interval to a discrete entity, which means that we introduce a partition, let's say equidistant partition. So we decide that time moves in increments, which is actually a natural idea when you are, let's say, programming a computer game. You definitely have a time moving at regular increments there. So here is step size h, and these are some xi's. And now we take and look at the function that we're looking for, this function y, at these specific times, and we get some values, some numbers. So again, we have finitely many of them. That's a discrete situation. And we will call these numbers for xi. The corresponding value will be yi, capital Y. I'm reserving lowercase y for my approximations. Okay? So what did we just do? We took continuous function and we replaced it with just a finite set of points xi, yi. Suddenly, from a continuous situation, we have a discrete situation. But this function y, it's governed by a differential equation. So if you want to carry over this information, we have to find a discrete version of our differential equation. Because the initial condition, that's a discrete piece of information. We have a point here. That's okay. So how do we change continuous differential equation into a discrete object? Well, the differential equation is supposed to be valid at all points of this time interval. So instead, we will just look at it at these specific partition points. What do we get? Well, on the right, things are actually fairly simple. We substitute xi for x. We will just look at this right-hand side at these specific times. And then we have to put something for y, and we have the discrete version, capital Yi. So that was the right-hand side. That was easy. How about the left-hand side? Well, Now we don't know the function in the intervals between points. We have to make do with data that we have over here. Can we get information about the derivative from the data? And the answer is yes. We had a lecture about numerical estimation of derivatives. So I take this derivative and replace it with some approximation. For instance, the forward difference. Why not? So here we go. We have to look into the future. We are sitting here at point xi. We look into the future, which is yi plus 1. We subtract the current information, and we have to divide by the horizontal displacement, which is the step size, h. And this is not the derivative. It's not the same. There is some error, so we put it here so that we can write equality. What is the error? We actually don't have a formula for it, but we know how fast it disappears. It disappears at the rate OH. So this error is precise, but we don't know what it is, but it's hidden here. The precise formula or precise information is hidden under this notation. And this is the discrete version of our differential equation, one of possible discrete versions. So when we have this continuous situation, we change it into a discrete situation, and this is called discretization. Before we start doing any tricks, let me rewrite it, because we are really focusing on the future usually, so let me ask about the future. I'm going to multiply this equation by h, so it appears here and here, and then I isolate yi plus 1. What do we get? yi plus 1 is equal to yi plus fxi yi times h. I've been multiplying everything by h. And I take this capital OH, big OH, move it to the right, and it will be again OH. But I also multiply it by h, so it becomes h squared. And that's an alternative version of this equation which governs my solution. Discrete version of the solution is governed by this equation. The problem is that this is the exact description of the error which needs to be put here, but I cannot access it. Why don't I drop it? Can I drop it? Well, let's have a look at it. This term depends on h in a linear fashion, and this term depends on h in quadratic fashion. So for small h's, this term is negligible compared to this one, and therefore, yes, I can drop it. However, when I drop it, the equation becomes different, and therefore the numbers that I have as the solution will be also different. So from precise information about my solution, I am passing to approximation. Here we go, lowercase y, finally. So, when I'm looking for this solution of my problem, of my discrete problem, I instead pass to approximate solution. And this approximate solution is governed by such an equation. Now, this equation is very familiar. Of course, this is exactly the Euler method. What's more, notice that this is the local formula, passing from yi to yi plus 1. And therefore, when we analyze it, we learn about the local error. What is the local error? Well, actually, this is the precise equation. And when we pass to this one, we made an error, which is exactly what I'm looking for. And this error is of order OH squared. So the local error of this equation, of this Euler formula, is OH squared. And therefore, the global error is OH, which is an alternative proof that the Euler method is of order 1. Wonderful. So this discretization business actually gave us our starting method for Runge-Kutta exploration. Wonderful. And this is also a possibility to try something different. For instance, this was the forward difference. How do we approximate derivative using the backward difference? That's a good question. Well, it will have to go like that. yi minus 1 divided by h plus error term is equal to, and now we put the right-hand side into it, f xi yi. And now we can repeat the steps, which means we are going to isolate the data which is most to the right, yi, and we multiply by h, things like that. We pass to approximation by dropping this OH term, and we get yi is equal to yi minus 1 plus f xi yi times h. Now, we have yi minus 1, which is not very pleasant, so we shift the index by 1 everywhere, and what we get is the implicit Euler formula. So we don't want to worry about it too much, so that was a dead end so far. Let's try something more interesting. We notice that the quality of approximation of the derivative is related to the quality of the method that we get out of it. So why don't I replace the derivative in my differential equation with some estimate that is of higher quality? Let's have a look at it. How about the central difference or the symmetric difference? I have to look into the future. I subtract not the current but the previous information. I divide by the horizontal displacement. I am now comparing data in the future and the past, so the displacement is 2h. And we know that this approximation of derivative has local error OH squared. And on the right, we get f xi yi. The same game. We isolate capital yi plus 1. We have it there, good news. And then we drop the error term. So, yi plus 1 is yi minus 1 plus f xi yi times 2h plus oh cubed. This is the precise version, precise discrete version of our differential equation. Now we drop the error term, and this will be the local error, oh cubed, and we get yi plus 1, the approximate solution, is equal to yi minus 1 plus 2f xi yi multiplied by h, and that's it. I dropped the oh cubed part. And that's an interesting formula. Again, this is an iterative formula. If I know the past, I learn about the future. So I can use it repeatedly in a cycle to generate more and more points, just like we had it with the previous setup, with Runge-Kutta methods. So this is very nice, and it should be method of order 2, because the local error leads to global error OH squared. We just developed a method of order 2, but this is not a Runge-Kutta method, in particular because it uses information from the distant past. We are not just looking at the current situation, xi, yi, but also one step backwards. So here is the difference. Runge-Kutta methods, they look at the current situation at xi, yi, and then make prediction. What should be next? This new method works like that. It looks at xi, yi, and also at the previous situation, and then makes prediction. So these guys were one-step methods. You make one step forward, and this is called a two-step method. Two-step methods do exist, and they do not come only from this discretization. There are other ways in which they can be derived. So again, this is a representative of a huge group of methods for solving initial value problems. They generally tend to have a high order, but there is a little problem. How do you start them? You see, when you start constructing your solution, you only have the initial condition. You're sitting here, and you want to move. Now, for a Runge-Kutta method, this is no problem, because it's a one-step method, so you make one step. However, for this new method, you would need two pieces of data to make the next step, and you don't have them. Well, this can be handled in different ways. For instance, you can make one step, using a Runge-Kutta method. And now, since this formula has local error h cubed, it makes sense not to lose information to use, let's say, Runge-Kutta method of order 2, which has the same local error, so that you have it consistent. But it turns out it's not all that crucial because it's just one step, so you can also use, let's say, Euler method. This is really not a problem. And once you have two pieces of data, you can switch to this formula and continue. So this is actually a workable scheme. This method, by the way, does not have a name, and you will shortly see why. Let's play. What we have here is the differential equation which we used for testing our error estimates. And we know that this differential equation is not exactly easy because it's the one which has such a periodic solution with sharp peaks. And the Runge-Kutta methods, they had, okay, it wasn't totally bad, but they had a little trouble following those peaks. So let's have a look how this new method, two-step method, performs. And let's just have a look at the code a little bit here. We start at the original data, x naught, y naught, and then we have to make the first step. And when we look at the formula for the first y, this is just the Euler formula. Because we start at the starting level y, and we take the f slope multiplied by step size. So we are using ordinary Euler formula of order 1 for the first step, and then we construct all the remaining data. I'm actually not using any procedure here. You can program this easily, you just figure out a loop. Okay, let's have a look at this. What do I see in this picture? The, let's say, dark blue curve, that's the solution. Nice waves. Then we can see the red curve, which is down here. That's the Euler formula. Runge-Kutta method of order 1 for comparison. Of more interest is the blue curve, the light blue. It's supposed to be light blue. Yeah. It's not so easy to see the difference here. It's the broken one. That's actually the Hoyne method, method of order 2. Again, Runge-Kutta method of order 2. And the method that we created here, that's the brown curve which is going up and down. So it's zigzagging around, and actually the amplitude of the zigzagging is obviously larger and larger. So this is not very good. Okay, let's try to cure it. This was the step size 0.5, the one that we always use in all those experiments to have some comparison. Let's make it smaller. Let's say 0.3. So 0.3, the Euler formula got closer to the solution. Also, Runge-Kutta got closer to the solution. How about the brown curve? Well, in those peaks, it actually got close to those peaks. It got even closer than the Runge-Kutta method of order 2. So in those peaks, our method actually works better. But in those bands down here, it still oscillates, which is not very pleasant. And this is actually one of the reasons why this method is not used, because it tends to oscillate a lot. This is a big problem. Okay, let's try to pass to the step size 0.1, which is usually the next step size that we take to see performance for smaller steps. And now it looks really good. Okay, the Euler method still not good because it's method of order 1, and this example is actually fairly tough. But the other two methods of order 2, which means the Hoyne method and this guy, they're actually following the solution fairly closely. There is a tiny bit of a difference in those peaks. I can see here 3 different colors. It seems as if the line thickens at the peak. And over here, I can see 3 colors, but it's hard to say in which order. Okay, it seems to me that this new method is slightly closer to the solution. So it's a little bit better in those peaks. How about the bands? Well, when you look closely, you can see a little bit of wiggling. That's this new method. So it still wiggles, just the amplitude is very small. So definitely, as an approximation, it performs better than the Euler method, but only for very small steps. So this is the first sign that there may be something, let's say, fishy with this method. Let's pass to another example. If you remember, this is the equation which is close to exponential. The solution has asymptote at 1, and the specific solution for the initial value problem looks like that. And then, when we applied Runge-Kutta methods, the methods of higher order had a tendency to go away, and we had to cure it by going to small step size, and then it was okay. So here we had conditional stability. So we load the differential equation, and then we go back to the code above. I'm going to change the step size to 0.5 as usual to get a fair comparison. Here we go. So what do we see? The solution is dark blue curve, which has asymptote 1. The Euler method, that's the red broken curve, which has the usual troubles at those bends, but then it settles down to show the right solution. Then there is the blue curve, which goes away. That's the Runge-Kutta method of order 2, Hoyne method. And finally, we can see brown curve, which is oscillating wildly. Well, that's our new suspect. Okay, let's pass to a smaller step size. We want to cure those oscillations, 0.1. Well, what did just happen? The Euler curve got closer to the solution, and it's actually fairly good. The Runge-Kutta method, it's also very close to the solution. It sticks to it now. It doesn't go away. But the brown curve, the new method, keeps oscillating, and the amplitude seems to be increasing. This is very unpleasant. So let's try to decrease the step size to 0.01. And we can see that this oscillation is still there, and it actually sets off at roughly the same location. So there is something fundamentally wrong in the reaction of this method to our differential equation. Now, you look at a picture like that, and you may think, oh, wait a second. This two-step method is supposed to be of order 2, which is better than the Euler method. But the picture actually sends a totally opposite message. How is that possible? Well, the order is not about the magnitude of error. It's about the rate of its disappearance. That's an important distinction. Over here, for this two-step method, we have an oscillation which goes to infinity, huge error. And this tendency is fighting the quadratic tendency of disappearance of the error. And that's what we see in the picture, the fight of these two tendencies. When we change the step size, the picture changes in a specific way. Now, if we focus on a specific interval, which is what we have here in this picture, then sooner or later, even this huge error must disappear, because after all, this is a method of order 2. And if we go to really, really small step sizes, then this error for this two-step method will eventually become smaller than the error for the Euler method, because it is a method of higher order, this one. But the problem is that the initial error is so huge that you may need really, really tiny step sizes for this huge error to become superior compared to the Euler method. And perhaps you do not want to use such small step sizes because you are worried about numerical errors, things like that. So there is actually more to methods than just the order. You have to also consider stability, how they behave under different circumstances. And sometimes it actually may be more beneficial to use a method of lower order if a specific method of higher order actually behaves, let's say, not very friendly. But still, let's give this method another chance. Okay, how much time do we have? Let me try a step which I never try really, because it's very fine, 0.001. So, wow, that was fast. It's a good computer. Much better than mine at home. And we can still see this oscillation. I mean, I cannot cure it. As we go to lower and lower step sizes, the onset of the oscillation seems to be moving to the right. Yeah, now it's okay. So if we are interested in just a finite interval, then by passing to a really, really tiny step size, we can actually get a decent approximation of the solution also from this method. But the oscillation is still there. We can see it moving to the right. Okay, I will move slightly more to the right with my viewpoint. I will extend it. So this will be the same solution. We just see an extra part on the right. Yeah, there are those huge oscillations. So this method is not conditionally stable for this particular initial value problem. So that's why it doesn't have a name. Nobody uses it. So why did we look at it? Well, first of all, it's a representative of this interesting group of more step methods. You can have two-step methods, three-step methods, or you can have methods which always look at all the past which is available and make the next step. So actually the number of data which is being used increases as we move to the right with our approximations. So all kinds of tricks like that are possible, and some of the more step methods, they are very good. So this was an interesting, let's say, a door that opens to an interesting room full of interesting things. Another reason why I'm showing this is that the idea of discretization itself is very, very powerful. It did not quite work out for those simple initial value problems, but it really comes to its own when we pass to differential equations of higher order, or when we pass to partial differential equations with partial derivatives. So for more difficult problems, which are actually the real-life problems, this discretization idea becomes very, very useful, and it leads to a method which is called finite difference method. This is actually a finite difference method. When you replace derivative with a finite difference, you are in fact applying a finite difference method. Okay, that's it for this first interesting approach. We are not going to milk it anymore because it doesn't seem to work all that great. So let's pass to the second interesting approach I want to talk about today. We start by recalling the original idea for the Runge-Kutta methods. We are sitting somewhere. Here is the solution. And we decided to move using a tangent line of the solution. And in this way, we've made our next step. What is a tangent line? Now, you can answer this question in several ways. And one possible answer is that the tangent line is actually a special case of a Taylor polynomial. It's a Taylor polynomial here, centered at this point, of degree 1. What happens if we try polynomials of higher degree? Well, they are bendable, so they have a chance of actually following the solution better. That's an interesting idea. Okay, what do we need for polynomials of higher order? We need higher order derivatives. Where do we get them? And the answer is we get them in the differential equation, because on the left we have derivative of y as a function of x, and on the right we have in fact another function of x. We can differentiate this equation, and when we do, we get a formula for the second derivative. Here we have to use the chain rule for functions of more variables. And when we do, we get something which does not look exactly friendly, but it's workable. Now for y prime we could actually substitute f, but this is not usually done. It's better to keep it as it is, and we can pass to the third derivative. So we differentiate this guy with respect to x and y and so on. We have to use the rules, and we get a formula which is becoming less and less friendly, to be frank. Because now we have to differentiate this part. And I differentiated the left part, and this is a product rule. So this is really becoming, let's say, slightly more complicated. So I differentiated this by x, then I differentiated this by y. And I have to use the chain rule. And this is the derivative of the first component. I have to multiply it by the second component. And then I have to copy the first component. And I have to take the derivative of the second component. Okay, I'm not going to try to develop formula for y fourth derivative. Anyway, this shows that it's possible to get information about higher order derivatives. But it's generally preferable to try it for a particular specific differential equation, because then you can hope for some simplification. You don't have to do crazy stuff like that. So let's have a look at the specific problem. Y prime is equal to minus 2x, y minus 1. That's the differential equation which was causing mild troubles. If you remember, it has a solution which goes like that. There is an asymptote at 1, and Runge-Kutta methods tended to go away until we made the step size really small. And the initial condition was y at 0 is 3. So that's the initial value problem. And this time, I'm going to go for Taylor polynomials of higher order, And for them, I will need some more derivatives. Notice that I know how much is y at the origin, and therefore, using this formula, I can also figure out the derivative. So the data, the flow of data goes like that, or the flow of information. I have this information, and using the differential equation, I figure out that the derivative at 0 is, let's see, x is 0, y is 3. 0, 3, well, that's obvious, 0. Now, I take this formula and I differentiate it with respect to x, and I have to remember that there is x hiding inside y as a variable. So y double prime is, okay, product rule. Negative 2, y minus 1, minus 2x times, and I differentiate the second term, and I get y prime. So, this is the formula for the second derivative, and it features y and also y prime, and at time 0, I have information about both. So, again, I use this information and also this information. I use all the previous information to obtain the value for the y second derivative at 0. How much is it? Well, x is 0, so this goes away. Y is equal to 3 to negative 4. Okay, let's take another derivative. Y triple prime. How much is it? Well, here I have to take derivative, which is obvious, minus 2y prime. And here we have to use the product rule, so we get minus 2y prime minus 2x y double prime. Can we simplify? The answer is yes. This is minus 4y prime minus 2x y double prime. Does it look nice? I would say yes. So, we know information about 0th, first, and second derivative, which is exactly the data that I need over here. So, what we get is, from this formula, that the third derivative at 0 is, and let's wait for it, 0 here, it disappears. And over here, we are putting the first derivative, which is also 0, we are getting 0. Wow, interesting. Okay, let's go for the fourth derivative. 1, 2, 3, 4. Okay, I differentiate minus 4 y double prime, and I use the product rule, minus 2 y double prime minus 2x y triple prime, which is minus 6 y double prime minus 2x y third derivative. And again, I need information at 0, which I already have here. So from the information, I get that the fourth derivative at the origin is, okay, x is 0, and the second derivative of y, when I look at it, this looks like 24. Here we go. Interesting. Okay. I guess that's enough. I have information over here about the first 4 derivatives of my solution at the point 0, which is the starting point here for my exploration. So I can form all kinds of Taylor polynomials. For instance, knowing the derivative, I can form the polynomial T1. T1 is just y0, which is 3. And the linear term is missing. I can also form T2. T2 is the value plus the linear term, which is missing, and then there is the quadratic term divided by 2 factorial, so we get minus 2x squared. Using this information, I can get T3, which is actually the same because the cubic term is missing. Finally, we are getting to T4, which is 0th term, linear term is missing, quadratic term is this, cubic term is missing, and now for the term with the 4th power, x to the power 4, what do we see there? We see the plus sign, and we have to take this number and divide it by 4 factorial. How much is 4 factorial? 2, 6, 24. I'm getting just this. The coefficient is 1. That's wonderful. That's a nice polynomial. So I just derived polynomials of various degrees, and I have to make a choice. Which one do I want to use? Well, I don't know. Let's say this one, quadratic. Okay. So I decide to follow my solution using T2. And I get approximation on this range. And I will say, oh, wait a second. We are playing with some specific partition for the x variable. So we are going here to some location h. And here we are looking for an approximation. How do we get it? It's easy. We look at x1, and we substitute it into the polynomial that I chose, into T2, and I get my y1. So what is step h? That's a good question. Let's try h equal to 0.5. So when h is 0.5, let's say that I choose to use T2, and I get y1. Okay, x1 is 0.5, and y1 will be, I take 0.5 and I put it here. This becomes 1/4 minus 1/2. This is 5/2. That's my approximation for the solution at location 1/2. If I used T3, I would get the same thing. If I used T4, I would get another answer, okay, different y1. What do you do next? Well, you just move this whole situation to the right. You are sitting at this point, x1, y1, and you want to construct a Taylor polynomial there. Can you do it? Well, notice that these formulas for derivatives, they're universal. I didn't know when I was deriving them that I am doing this at location 0. So these formulas are general, and now I'm sitting at the point x1 with value y1. So that's exactly the type of information I had here. Y at 0.5 is 5/2. This is actually the approximation of the solution y, but we are now following a different solution. We talked about it. Local method again. We know y. We can substitute into the differential equation, and we get y prime. So just by substituting into the given equation, y prime at 0.5 is, and let's see, 5/2 here, 3/2 times 2 is 3, times x is negative 3/2. We know y. We know y prime. We have enough data to use the formula which I'm going to call star, so that I can refer to it. And this yields the second derivative at 0.5. Do I feel like calculating it actually? Let's see. 5/2 minus 1 is 3/2, times 2 is negative 3. And here, y prime is negative 3/2. Another one here, this is 3/2, this is 3/2. Negative 3, okay, I think it's negative 3/2. Perhaps I've made a mistake. I don't care. This is not really crucial. Now I have enough data to substitute into double star formula. So substituting into the double star formula, I obtain the third derivative at 0.5, and so on. So you can see, using these formulas and the starting point information, again, there's a cascade of information flowing down. It provides me with exactly the same data that I need for the Taylor polynomial centered at 0.5. And I can write it down. I can write the polynomial. T2x will be the starting value, 5/2, plus the linear term, which is actually minus, okay, minus 3/2, and I have to be careful, x minus 0.5, and then there will be the quadratic term, so again minus 3/2 divided by 2 factorial, this is 3/4, x minus 0.5 squared. And this is a quadratic polynomial which is centered at 0.5. So here there is some sort of a parabola, and when I look at the sign over here, actually it's going downwards because there is minus in front of the quadratic term. So there is a parabola going down, and I will follow it, making another step of size h. So x2 will be 0.5 plus h, which is 1, and y2 is obtained by taking this t2, but it's a different t2 compared to this one. Hopefully things are clear. So I take this t2 and I substitute 1, the new x, for x, and I get some value. And this will be a new point, and I start the whole business again, going forward by Taylor polynomials of order 2, or 3, or 4, and so on. So this is something which can be done, and this is called the Taylor method. Let's have a look at it. So I'm loading my test example, which is again this differential equation, this one, which caused mild troubles, so we will see. I have to set up coefficients. So here is a procedure which calculates the first derivatives, 2 minus 2y, that's this part, 2 minus 2y, minus 2x and the derivative. Okay, so the first line, that's the second derivative. And then I differentiate it again, and I get a second line. Minus 4 derivatives, this fits, minus 2x, second derivative, this fits, okay? So these are the derivatives which are calculated here. Maple did it for me and created a procedure based on it. And now I look at what's happening at the origin, at 0. And in the picture we can see the solution, which is the dark blue curve going to the right with asymptote 1. And we can see several curves. We actually see 3 curves, although we are not aware of it. We can see polynomial t2 in red, but we don't actually see it because it was merged with polynomial t3, which is in green. So this green curve, it's common for t2 and t3. It's a parabola which is actually showing downwards. That fits, so the shape is correct. And for t4, that's the dark blue curve, or light blue curve actually, whatever. Yeah, it's a light blue curve going upwards. That's this polynomial. It's a polynomial of order 4, and it goes upwards because there is plus in front of x to the power 4. So this all fits. These are the 3 polynomials that I can choose from, and of course there is also the polynomial of degree 1, which corresponds to the Euler forward method. Yes, t1 is the tangent line. So that's what the Euler method would use, just 3. Now I have to choose one of these polynomials, and I make half a step forward. So I choose a point which is located half the way between 0 and 1, and that will be my new center. So I just did. Here we go. I decided to use x new 1/2, and let me look at the code. For new y, I'm using t2. Okay. So really, what I did over here, I chose t2. I'm doing exactly the same in my Maple code. And then I calculate new coefficients, and I create new polynomials. Here we go. By the way, the new value for y is 2.5, which is exactly 5/2. Okay, things agree. So what we see here is the 3 polynomials which I would generate, t1, t2, t3, t4. Actually, t1 we don't see, because that's the Euler method. Boring. t2, that's the one that we want here. It's the polynomial in the red, t3 green, and t4 light blue. And they are all based, they have a center, okay, let me try to do it like that, over here at 1/2 and 5/2. This is the center for those 3 Taylor polynomials. They are sitting at that point, and again they are moving. And I can choose again, okay, what will be my new x? My new x, I'm going half a step farther, my new x is 1. So let's have a look at it. Here is the code. This time the center is at 1, which is somewhere here. And this is the starting point for 3 polynomials. And again, we can choose, we chose actually t2. It doesn't make sense to switch polynomials. So I'm showing the other guys just out of curiosity, just to see how they go. So as you can see locally, they're actually describing the solution quite well, and only later on they go away. So when we keep the step size reasonably small, this should work okay. And we keep going like that. Of course, we have a procedure for that. So here we go. I decided to use quadratic polynomials, which is a good idea. Here we go, step size 0.5, and this is the picture. And we can see that the solution eventually departs, which is exactly the same thing which was happening with higher order Runge-Kutta methods. So this is a good example. By the way, since I was using Taylor polynomial of degree 2, this is a method of order 2. And it works like that. If I decided to use T3, I would obtain a method of order 3, and so on. So these Taylor polynomials, they offer me a nice direct way to methods of arbitrary order. Just when you want to go to higher degrees of polynomial, you have to make formulas for a higher degree of derivative, which can be tiresome. But it's another story. So this is nice. As usual, the picture is misleading. Those connecting segments, they have nothing to do with the solution. They are just there to, let's say, emphasize the points. The points, that's the key. Now, this procedure is actually nice. I designed it in that way that I can do something which you pretty much never see. If you are curious about how these points came about, they came from some approximating Taylor polynomials. Well, we can ask for it. Let's have a look at it. For the output, I change it to full graph. And we can see that to get from one point to another, we were following parabolas. That's nice, isn't it? Okay, let's try to take smaller step size. Because 0.5, that's like the default for comparison, and then we always go lower. So let's say 0.1. Wow, that looks nice. So similarly to Runge-Kutta methods, passing to step 0.1 cured the problems. The Taylor method works really well. What happens if I keep the original step size and I increase the degree of the polynomial to 3? Good question. And the answer is we can again see this departure, but it actually happens a little bit later. So this is an improvement. Even with a step 0.5, things get better. Generally, improving the degree has a better effect than lowering the step size, which is a good news, because when you go to extremely small step sizes, you run into troubles with numerical precision, with round-off errors, things like that. So we prefer to keep larger step sizes and increase the degree of the polynomial. But this increases the computational complexity. So let's say a compromise between precision, good precision, and the amount of work that you have to put into it seems to be T4. This is very popular. So let's go to degree 4. And we can see the departure at the end. It's still there, but otherwise, yeah, it looks really good. Okay, we had another problem which was, let's say, less easy for differential for numerical methods to handle, and that was the problem where the solution was periodic like that. So let's have a look how the Taylor method handles this case. We load the differential equation, and again, the starting step size will be 0.5, which is, let's say, unreasonably large, but for comparison, we use it always, so we will see. And the first degree that I chose is degree 1. So we will be actually using tangent lines, which means we will be using the Euler method. Here we go. And this is the picture that we have seen before when we were developing formulas for approximating errors. Exactly this picture. It behaves as expected. Now, let's move to degree 2. So this is Taylor method of degree 2, which means it's a method of order 2. And this is actually a fairly good approximation. And for the step size 0.5, this is better than the Hoyne method and the midpoint method, the Runge-Kutta methods of order 2. So this shows the Taylor method in a good light. Okay, how about going for degree? Well, let's go to 4. I said it's popular, so let's try degree 4. Wow, this is almost a perfect match, despite the step size 0.5 not being all that great. So you can really see that the effect of higher degree is very pronounced. So T4, very good method, even with large step size. Let's go back to degree 2. Quadratic Taylor polynomials, and let's try to decrease the step size to 0.1. And again, we are getting a very good match. So it seems that the Taylor polynomial is actually capable of providing better approximations for reasonably large step sizes. And indeed, that's the experience. So when you want a really good approximation, the Taylor method seems to be a good idea, but it's really hard to work it out. So you need to put more effort into it, and the computer has to put more effort into it. So that's how it is used. Taylor method is usually reserved for those situations when you really want high precision. If, let's say, slightly lower precision is still okay, and your priority is in getting it fast, then the Runge-Kutta methods are a really good compromise. Now, before we move on, we had this example, the giant killer, differential equation and an initial value condition that led to the sine function as a solution. And every method that we tried sooner or later departed. And I said, this is working always like that for numerical methods. How will the Taylor method, which is supposed to be really good, handle this example? Let's have a look at it. So this is the differential equation. And we start with the quadratic Taylor polynomials, degree 0.5, and the solution does depart. We are not surprised. And going for smaller step sizes, let's go to 0.05. Let's skip the intermediate sizes. Yeah, it's bad. How about 0.005? Well, perhaps this is too much. Oh, I may have overdone it. Okay. Well, you can see here that the Taylor method really works hard for the results. So that's what I've been talking about. We are looking for a compromise. And quite frankly, okay, here it is. Yeah, still didn't help. So we go back to the step size 0.5 so that we can see the result quickly. About degree 4. I promised that this one is supposed to be quite good, and it does depart. Decreasing the step size to 0.05. Well, again, we are working harder. It's still bad. So my favorite giant killer initial value problem also handles easily the Taylor method. It shows that it's not good enough to handle this beast. And that's it. But don't switch the dial, because in this Taylor procedure there is something interesting hiding, and I want to show you because I think you will like it. I'll be right back. Okay, here we go. We are sitting at the starting point, 0, 3. And we are trying to move to the right using Taylor polynomials of various degrees. Now, experience tells us that if we go for higher degrees, then we get better approximation nearby, but also the region where the approximation is reasonable extends to the right as we go to higher and higher degrees. So why don't I try higher derivatives? Now, this is boring, so let's try to guess a formula. When you look at it, it's always minus 2x and some derivative. Because when you take derivative using the product rule, you differentiate the second part and keep the first part. So with the second part, it will always be here, like that. So how about the kth derivative? The kth derivative should always have the term negative 2x, y, and the derivative is lower by 1. So the derivative will be k minus 1. How about this term? Well, for every derivative, when we apply the product rule here, we differentiate to x, and the derivative matches with the new derivative here. So it keeps adding 2 to the coefficient. So definitely it will be double, and with minus sign. And there will be a derivative of a specific degree, namely k minus 2. It's lower by 2. And now we multiply this 2 by a special coefficient that has something to do with the order of the derivative. Does it work that it's a double? The answer is no, because here is the third derivative and the number is 4. For fourth derivative, the number is 6. So it's not a double exactly, it's shifted by 1. 6 is double of 3, 4 is double of 2, and so on. So I think if I put k minus 1 here, it will fix it. Does it work? Let's say for the second derivative, k is equal to 2, so it's 2 times 1 is 2. Yeah, that fits. Okay? So that's the formula, recursive formula, and therefore we can generate the result fairly easily. But what's more important, we need those coefficients. And this is where it gets, let's say, tricky. Because when you look at these numbers, 3, 4, 24, it's not quite clear what's happening there. Okay. The odd derivatives, they are all zeros, and actually if you try to do a few more derivatives, you will see that this is true. So when you differentiate at the origin, the odd order derivatives, 2i plus 1, yield 0. The real question is, what are the even degree derivatives or even order derivatives? And what we can see is that the sign is changing. 3 minus 4 plus 24. If you go for the sixth derivative, it will be negative again. So there is negative 1 to I or I plus 1. We will see. When I is 1, so it's the second derivative. When I is 1, the sign should be negative, so it works with I. I don't have to shift it. That's good. Okay, what else? Well, actually it's not easy to see it. One has to work it out from this recursive equation. So, yeah, this is actually quite hard. What's happening is that when you put 0 into it, this term disappears, and the y derivative has a formula which goes by powers of 2. So you are getting actually a recursive formula which goes like that. The kth derivative at the origin is just negative 2 times k minus 1 times derivative at the origin of order k minus 2. So every time you increase the derivative, the minus sign changes here. That's true. Then there will be a factor of 2 appearing. And then there are those k minus 1s appearing and multiplying each other. So there will be something with factorial. But it's not quite clear to see at the first sight how it works. I actually worked it out at home. And I got the following formula. Let's have a look at it. It's 2i factorial divided by I factorial multiplied by 2. I don't think it's possible to actually just guess it by looking at this string of results. For which i's is it true? I used this recursive formula to derive this result, so I'm pretty sure that it works for the fourth derivative, which means when I is equal to 2. Let's check. When I is equal to 2, we are getting fourth derivative. And the answer should be 24. When I is 2, this is 4. 4 factorial is 24. Divided by 2 and multiplying by 2 is 24. And positive sign. This works. How about I equal to 1, which gives us the second derivative? When I is equal to 1, this is 2 factorial, which is 2, divided by 1 times 2 is 4, negative 4. So it also works for 1. How about the 0th derivative? This is the case I is equal to 0. Well. How much is this formula when I is equal to 0? I look at it. 0 factorial is equal to 1. 0 factorial is equal to 1. So it's 2. Yeah, just 2. Does it fit? No, it doesn't. So this formula is only valid for I at least 1. In this way, we determine all the derivatives that we need for our Taylor polynomials, so we can construct Taylor polynomials of arbitrary degree. Why don't we just simply take Taylor series? Because a Taylor series, with a bit of luck, precisely describes the function that we are trying to find. Taylor series, how does it go? I will optimistically call it yx, because I'm hoping that it will provide me with the solution y. Well, k goes from 0 to infinity, the kth derivative of my function at 0 divided by k factorial multiplied by x to k. That's the general formula. Now we look at the derivatives and we see that the odd powers, they all drop out. So we'll be just looking at even powers, which will be encoded by taking k equal to 2i. I ranges from 0 to infinity. Now we want to use this formula, but we can see that for I equal to 0, it does not quite work. So we have to take the 0th term separately, put it like that, and then we take summation I ranging from 1 to infinity, and for the derivative we substitute this expression. So it's negative 1 to power I, 2i factorial divided by I factorial times 2. And then this has to be divided by the k factorial and k is equal to 2i. So we are dividing this by 2i factorial and x to k, which is 2i. Okay. Before we go on, what's unpleasant is that this series starts at 1, not at 0. So what I'm going to do, I'm going to take this 3 and split it as 1 plus 2. 1 stays away, and 2 can be included in the formula because 2 is actually the value of this expression for I equal to 0. So let me just write it. This is 2 times x to the power 0 plus summation I going from 1 to infinity. Okay, what I see number 2 here. So this is similar. Let me keep it like that. 2i factorial cancels. I can see negative 1 to I, and I can see 1 over I factorial, and I can see x to 2i. Now, does it fit? That's an interesting question. When I is equal to 0, 2 is 2. This is plus 1. This agrees. This is 1. It's also here. And x to 0 agrees. So I can use just one summation, I going from 0 to infinity. I can, okay, let me keep 2 over here. I will put 1 over I factorial here, and I will collect some stuff into the power. This is actually negative x squared, that all to power I. When we multiply out again this power, we will see that it's the same. Negative 1 to I, x to 2i. So far, so good. Now, let's see. We are almost there. I factor out 2. This is a summation I ranging from 0 to infinity. And in the summation, we can see fraction I derivative in the denominator and negative x squared to power I in the numerator. And that's a series that we know. This is the series expansion for the exponential function with argument negative x squared. By a remarkable coincidence, that's exactly the solution that we are looking for. That's the analytic formula. So by trying to pass from Taylor polynomial and the numerical method to Taylor series and analytic point of view, we actually obtained solution to our problem. This shows that the Taylor expansion can be actually used to solve differential equations, and that's a topic that we will revisit when we learn about higher order differential equations, things like that. This is also an interesting door that one can look through and see, oh, wow, it's interesting there. Do I want to go there? We will, definitely. And that's all for today. So see you next time. By the way, an interesting question. When you see a picture like that, you may wonder, how about now before, okay. Now, actually, before we move on, interesting question. This is a method of order 2. Shouldn't it be better than Euler? I mean, this is not better than Euler. What's happening there? And the answer is, again, now you may wonder, how is this possible?